Up until this point in this unit, we've been studying 3 different gas laws. We used Boyle's law to compare pressure and volume, and we noted that pressure and volume are inversely related. We studied volume and temperature with Charles's law, and we discovered that they are directly related. And finally, with Gay-Lussac's law, we studied pressure and temperature, and we noted that they were also directly related. Now what we're going to do is we're going to combine all of those gas laws together. Now, if you remember from Boyle's law, we had said that your initial pressure times your initial volume equals your new pressure, P2, times your new volume. All right. Now, if you look here, if I need to incorporate temperature, think about Charles' law. Charles' law tells us V1 over T1 equals V2 over T2. So to create my combined gas law, all I'm going to do is put P1 V1 over T1 and P2 V2 over T2. So this is my combined gas law. It's actually nothing new. It's just combining all of those gas laws together. Now, an interesting thing that this table does for us right below right here is it shows us when we use certain laws based on the combined gas law. So for example, if our temperature stays the same, so let's say this was, it doesn't really matter, 200 Kelvin and 200 Kelvin, you can ignore these two temperatures because they are the exact same, and so you end up with just P1 V1 equals P2 V2, which is Boyle's law. The exact same thing happens if your pressure stays constant. If your pressure stays constant, then you have V1 over T1 equals V2 over T2, and you have Charles's law. Finally, if volume stays constant, then you have Gay-Lussac's law. So with each of these, one measurement, whether it's pressure, volume, or temperature, will stay constant. If it doesn't, if pressure, volume, and temperature are changing, that is when you will use the combined gas law. So let's look at our first example. What it tells us is that a child has a toy balloon with a volume of 1.8 liters, and so I'm going to really quickly mark this as my V1, my initial volume. The temperature of the balloon when it was filled was 20 degrees Celsius. Now remember from Charles' law and Gay-Lussac's law that this needs to be converted to Kelvin. This is my T1. And I'm actually going to do that really quickly. Remember the conversion between Celsius and Kelvin, you just need to add 273 to my degrees Celsius. So this would be 293 Kelvin. And a pressure of 1 atmosphere. So this is my P1. Now, if the child let the balloon go and it rose 3 kilometers into the sky, this 3 kilometers, guys, is just extra information for you. The pressure becomes 0.667 atmospheres. So this is your P2. And the temperature is negative 10 degrees Celsius. Now, that will be my new temperature. That's my T2. Again, remember, I need to be in Kelvin, so I'm going to take 273 and add negative 10 degrees to that, and that'll be 263 Kelvin. And what it's asking me to find is the new volume of my balloon, so my V2 is what we do not know. All right, so I'm going to set this up for you, and then you guys will actually solve it. So I'm going to, if you notice, my pressure is changing, my temperature is changing, and my volume is changing. So I'm not going to use one of these 3 gas laws in which only 2 things are changing. I need to use my combined gas law. I need to use this guy right here. All right, so I'm going to write out the formula. P1 V1 over T1 equals P2 V2 over T2. And I'm going to plug in my values. My P1 is my 1.00 atmospheres. Okay. My V1 is my initial volume, which is 1.80 liters, all over my T1, which is 293 Kelvin. And that equals my P2, which is 0.667 atmospheres, times, I don't know what my V2 is, all over my T2, which is 263 Kelvin. So what I want you to do right now is pause this video and solve for V2. With the gas laws that we've been studying thus far in the unit, we know the relationship between pressure, volume, and temperature. But there's one measurement that we studied extensively in the last couple of units that we have not addressed, and that is number of moles. So there is another gas law that allows us to consider this. It's called the ideal gas law. And the assumption that we're making with the ideal gas law is that gases are not attracted to each other. The molecules are not in any way attracted to each other. So those assumptions from the kinetic molecular theory that we looked at the beginning of the unit come back into play. Now, with the ideal gas law, I'm going to write out the formula for you. It is pressure, okay, times volume equals N times R times T. So there are 3 old terms in this that are a review, and there are 2 new terms. This right here is obviously your pressure. V is your volume. Okay. T is your temperature. Temperature. Okay. The 2 new terms that we're going over are your N, which represents your number of moles, and then R is what we call your ideal gas constant. So this is your ideal gas law constant, and the value of it is 0.0821. And here's the important part. The units are liters times atmospheres all over moles times Kelvin. The reason why this is important, these units tell us what every other measurement needs to be in. So for example, volume must be in liters. Pressure must be in atmospheres. Number of moles obviously must be in moles, and your temperature must be in Kelvin. All right, so what will happen in this problem, I will give you 3 of the measurements, either pressure, volume, number of moles, or temperature, and we'll ask you to solve for one of them. So I'm going to show you one of the example problems right now. In the question it says, if I have 4 moles of a gas at a pressure of 4,256 millimeters of mercury and a volume of 12 liters, what is the temperature? So in this problem, I'm solving for temperature. As I write out this problem using PV equals nRT, also called Pivnert, I need to make sure I'm in the correct units. So 4 moles, I'm good because I want my units to be moles. Pressure, unfortunately, that is not the correct units. I need to be in atmospheres. So I'm going to quickly convert this. 4,256 millimeters of mercury. I need to get into atmospheres, so I'm going to crisscross. For every 1 atmosphere, there are 760 millimeters of mercury. And so what you need to do is divide. When I divide 4,256 by 760, I get 5.6 atmospheres. So that's the pressure I will use because I need to be in atmospheres based on my R, based on my constant. Volume is in liters. I'm good with that. That's liters. And now I can solve for temperature. So my pressure is 5.6 atmospheres. My volume is times is 12 liters. My number of moles is 4 moles, times my R, which is 0.0821 liters atmospheres over moles Kelvin, times my temperature, which I'm trying to solve for. So what you should notice, what I'm going to have to do is take my pressure times my volume, and then I'm going to divide that by my 4 moles, my 0.0821, that constant. If you notice, atmospheres will cancel, liters will cancel, and moles cancel. And so I'm left with my unit for temperature, which is Kelvin. So take this right now, 5.6 times 12, and then divide by 4 and divide by 0.0821, and let me know what your temperature is. And that's your ideal gas